Have you ever just stopped and wondered what keeps our modern world, well, running? I mean, everything from the fuel in your car to the medicine you might take. There's this hidden engine, this invisible intelligence working behind the scenes everywhere. Well, today, we're going to pull back that curtain. We're diving into process control.
So let's kick things off with a little puzzle. What on earth do rockets, a good beer, and life-saving drugs all have in common? I know, they seem like they're from totally different universes, right? But the answer, well, it's the very thing we're talking about today.
So here's our game plan. First up, we'll get down to the basics. What exactly is process control? Then we're going to see it in action in some pretty surprising places. We'll look at what it's trying to do, the real-world challenges engineers have to deal with, and finally, how we make these systems smarter, safer, and faster. Let's jump in.
All right, part one. What is process control? You'll be surprised. At its core, it's a really simple idea that has a huge impact on pretty much everything we do.
So what are we talking about here? The textbook definition is that it's the automated regulation of variables, things like temperature, pressure, or how fast something is flowing, to hit very specific goals for safety, quality, and efficiency. Honestly, the best way to think about it is like an autopilot for industrial processes, always making these little tweaks to keep everything humming along just right. And this is how it works. It all comes down to this basic continuous loop. Let's take your water heater at home. First, you set a target, right? You want that water at, say, 75 degrees Celsius. Then, the system uses a sensor to measure the actual temperature of the water. Next, it does a quick calculation to figure out the difference, the error, between what you want and what you've got. And finally, based on that error, it takes an action to correct it. It turns the heater on. This simple set, measure, calculate, correct cycle is the absolute foundation of almost every control system out there.
Okay, so now that we've got the basic idea down, let's go see where it shows up in the real world. We're going to take a quick tour and find process control hiding in plain sight. Think about pharmaceuticals. When you're making medicine, every single pill has to be exactly the same and perfectly safe. Process control is what automates the super precise mixing, the temperature, the dosing, all to guarantee that every batch is identical. This isn't just about quality control, it's about our safety, making sure every dose has the exact same strength.
And hey, it's also in the fun stuff. Take beer brewing. Advanced controllers manage the fermentation temperature with incredible accuracy. This doesn't just speed things up, it actually makes the beer taste better and more consistent. So yeah, next time you're enjoying a cold one, you can give a little nod to process control. Now let's go big. Our entire energy grid depends on this. In oil refining, predictive control systems are working constantly to optimize fuel purity. And get this, in wastewater treatment plants, there are now AI-driven systems that can actually predict pollutants and adjust the treatment on the fly. It's making the whole process way more efficient.
And of course, you see it everywhere in modern manufacturing. Those high-precision robotic arms that build our cars and our phones. They rely on really sophisticated nonlinear controllers to pull off these complex jobs with a speed and accuracy no human ever could. It's the invisible brain guiding all that robotic muscle.
So we've seen where process control is used, but let's talk about the why. Why is it so absolutely critical? Let's break down the main goals of any control system. So what are these systems actually trying to accomplish? It really comes down to four key things. First, stability. You want to keep the process steady and predictable, no wild swings. Second, accuracy. You've got to hit your target number precisely every single time. Third, and this one's huge, safety. Making sure everything operates within safe limits. And finally, efficiency. Using the least amount of energy and creating as little waste as possible. But here's the thing. Not all controllers are created equal. You have to match the tool to the job. So on one side, you have your classic PID control. It's the reliable, old-school workhorse. It's perfect for a simple job like a water heater, which just needs to hover around a certain temperature. But on the other side of the spectrum, for something incredibly complex and high stakes, like keeping a rocket pointed in the right direction, you need something way more powerful. That's where Model Predictive Control, or MPC, comes in. It's predictive, it can handle a bunch of different constraints at once, and it reacts in a flash. Because with a rocket, even a split-second mistake can be, well, a very big problem.
And when you really nail that efficiency goal, the results can be absolutely jaw-dropping. Look at this number, over 80%. What is that? That's the actual energy savings from a smart cooling system on a gigantic ship.
Instead of just running the pumps at full blast 24/7, adaptive process control figures out exactly how much is needed, slashing electricity use. That is the real-world power of smart control.
Of course, none of this is as simple as just plugging it in. Getting these systems to work in the real world means facing some pretty big hurdles on the factory floor.
Yeah, engineers have their work cut out for them. First, there are computational limits. A really complex controller can literally overwhelm the computer hardware it's running on. Then you've got network latency. Even a tiny delay in communication over a network can mess up the whole system. You also have to deal with sensor noise, getting fuzzy, inaccurate data which leads to bad decisions. And a massive one today is cybersecurity. As soon as you connect these systems to a network, you have to lock them down tight to protect them from attacks.
So, with all those challenges, how do you get it right? Well, that brings us to our last section, the best practices for building control systems that are truly smarter, safer, and faster. To really succeed, the experts focus on 4 key things. First, like we said, you have to match the controller to the job. Don't overcomplicate it. Simpler is often better. Second, you always validate with simulation before you go live. Think of it as a virtual test flight to catch any bugs in a safe environment. Third, for the really tough nonlinear problems, you can use hybrid designs that mix and match the best parts of different control strategies. And fourth, you instrument for the future, building in sensors that let you do predictive maintenance so you can fix things before they break. And this quote just nails it. This isn't about some quick fix. Following these proven best practices is what makes a system work reliably and efficiently, not just on day one, but for its entire life. And that leads us right to the future. We're already seeing amazing tech like AI and the industrial Internet of Things making these control systems smarter than ever before. So I'll leave you with this to think about. As this technology keeps getting better and smarter, what's the next big process in our world that's just waiting to be automated? What's the next unseen engine that we're about to build?